Hey guys, and welcome back. Today we're going to be comparing linear functions. So in order to do that, we have one success criteria. In fact, in the learning target itself, we're finally getting down to actually doing what this learning target is intending, and that's comparing the rate of change and initial value, and also to interpret their meanings in context. We've done quite a bit of interpretation so far, so hopefully that's not something that we need to be focusing on, but we're going to compare rates of change and initial value. So in order to do that, in order to compare, we're going to need to make sure we can identify the slope or the rate of change and identify the y-intercept in lots of different forms. That's the only way we're going to be able to compare it. So let's take a look at a little introductory here. It says the graphs of two linear functions intersect if the functions have different rates of change. So notice how these two blue lines, they intersect. And the reason why they intersect is because their rates of change are different. If rates of change are the same, that means they have the same steepness, and thus would either be the same line or be two parallel lines. And again, on this graph over here, they intersect because their rates of change are different. So we're going to focus on what rates of change are greater than others, and we're going to have to keep in mind negative numbers because negative numbers may not necessarily mean that something is changing more quickly. So let's take a look at this first example. It says for each city, there's a linear function that describes the temperature in degrees Fahrenheit in terms of number of hours since 8 a.m. Which function was the greatest rate of change, and what does this mean in the situation? So let's take a look at these three different cities. We're looking at their weather reports. And they're represented in three different ways. We have the word problem, which I've often called a context, okay, which is Eastbury. So we have to pick out the rate of change just from the words. Topperville actually gives us an equation. And Hilltown gives us a table. Just writing it sideways so you guys realize we are comparing rates of change in three different ways. So let's try to pick out the rate of change in Eastbury. In contextual problems, remember that the initial value is what they start with. So if we're going since 8 a.m., it says at 8 a.m., the temperature was 62 degrees. That to me indicates what it started at, because again, we're starting at 8 a.m. So this is the initial value, or the b in y equals mx plus b. As far as the rate of change, notice the word per. Okay, the word per should indicate to you what the rate of change is, which they say is 3 degrees Fahrenheit per hour. So I'm going to point to that as well, just to indicate that the 3 is our m in y equals mx plus b. I can even create an equation if I wanted to and write it right next to Eastbury's sign here. It should be y equals 3x plus 62. And I usually make an equation just so that I can see the slope and the y-intercept next to each other, but you don't have to create the equation in order to compare. So let's take a look at Topperville now. Topperville has their equation written in terms of t and h rather than in terms of x and y. That's okay. If we were to say which variables would equate to h and t, we have t is equal to, I'm going to switch these two numbers just so that you can see y equals mx plus b. We have t is equal to 2h plus 54. So really the t is acting like the y, and the h is acting like the x. Okay, so in this case, the 2 is going to be our rate of change because that's sitting next to our, quote, x value or our multiplier, whereas the 54 is going to be our y-intercept. So now all we have to do is identify the rate of change in the table. So just like we always identify rate of change in a table, we need to notice how the x's are changing and how the y's are changing. The x's are going up by 1 hour at a time. It goes from 6 to 7, 7 to 8, so it looks like Each time we're just increasing by 1 hour. Whereas on the temperature side, I see 58 to 60, that's adding 2. 60 to 62, also adding 2. Okay, so it looks like every hour that passes, the temperature goes up 2 degrees. So if I want to create an equation out of this, I would say y is equal to, my rise would be 2 over 1, so that's just 2x plus my initial value. Since we're starting at 8 o'clock, this is where this problem gets tricky. Don't go for this guy right there. Okay, just because it's the first thing that's listed, that doesn't mean it's the initial value. It says we're going from 8 a.m. So where we would start looking at those temperatures should be at 8 a.m., which is 62. So I would say this equation is y equals 2x plus 62. And now we're ready to compare. Which function has the greatest rate of change? I'm seeing Eastbury has 3, Topperville has 2, and Hilltown has 2. So as my answer, I'm going to say Eastbury has the greatest rate of change. The second question says, what does that mean in this situation? Okay, so think about what these charts and contexts and equations are telling us. It's talking about 3 cities starting at a certain temperature and then increasing in temperature as hours go by. So this rate of change, the meaning, and I'm going to write that down as well. You guys need to practice writing this down as well. Don't just skip over this. Means for every hour that passes, we'll say Eastbury, or Eastbury's, possessive, Eastbury's temperature increases by 3 degrees. And notice how every time I have to write what a rate of change meaning is, it's going to be 2 units. So for every hour was one of the units. Okay, for every hour that passes, Eastbury's temperature increases 3 degrees. So the hours are changing and the temperatures are changing. Rate of change, there's always 2 things that are changing, an X and a Y, an input and an output. So let's have you guys take a look at something similar on your U-Try. Alright, so I've actually got one more U-Try that I'd like you guys to do, but I want to make sure you guys know what this question is asking you to do. It says, here are the rates of change for the 3 temperature functions from, and this should say the first example, so this is from example 1. If you graph the 3 functions on the same set of axes, what will be true about the lines that represent Eastbury and Hilltown? What will be true about the lines that represent Hilltown and Topperville? Explain. So let me go back to the slide where it talks about the different rates of change. It says if graphs of 2 linear functions intersect if they have different rates of change. Okay, so really all we need to do is calculate the rates of change for all of those cities, and if they're different, then they will intersect. So I want you guys to tell me what is going to happen with these cities. When it says what will be true for the cities, try to explain to me as much as you possibly can. So tell me which rate of change is going to be bigger, and then also tell me if the 2 lines are going to intersect. right, so let's take a look at a second example. We're still dealing with Eastbury, Hilltown, and Topperville, but this time it's going to ask us a little bit different of a question. It says for each city, there's a linear function that describes the temperature in degrees Fahrenheit in terms of the numbers of hours since 8 a.m. That's the same thing that we read before. Compare the initial values of the temperature functions for the three cities. What do the initial values mean? So just like we were describing rate of change, now we're going to be describing initial value. We did really all the work on these from the first example slide, so I'm just going to rewrite what I wrote as the equations in the first example. So Eastbury was y equals 3x plus 62. We had, let's see, Topperville was, instead of t and h, I'm going to write x and y. So y equals 2x plus 54. And then for Hilltown, we had y equals 2x plus 62. Okay, so now this time around, we're just comparing the initial values, or the y-intercepts. And once we make our comparison, we just have to say what that means, explain what it means in context. So I'm going to use this space right here. Looks like Eastbury and Hilltown have the same initial value at 62 for both of them, but then Topperville has an initial value of 54. So I'm going to write that. Looks like Eastbury and Hilltown have the largest initial values at 62. And now I just need to write what that means in context. So again, initial values are start points, and we're talking about temperature here. So this means that both Eastbury, that's an E, and Hilltown, their temperatures started at 62. Okay, so and I'm just going to mention those. You can say Topperville as well, but you would just be stating the same thing, that Topperville's temperature starts at 54 degrees. So remember, initial value is always the start point. All you have to describe is what it is the situation's talking about, and initial value is wherever it starts. So let's have you guys try this similarly on your U-Try. It's the same two cities you did in the U-Try from your last one, but this time it's going to ask you about initial value. So one of the main ideas here that we talked about is how if we have different rates of change, and that if we have different rates of change, that meant the lines were going to intersect. Well, here's an example of different rates of change, and different initial values. So not only are they going to intersect, but it will not be along the y-axis. So in the equations, you can tell, okay, we have -1/4. That's not the same as the number that would be next to x in the second one, which since there is nothing written, there is a 1 there. Okay, so -1/4 is not the same as 1. So these two lines are going to intersect. Now, since they have different initial values as well, that means they're not going to intersect on the y-axis. But if they do have the same initial values, you're going to see the two lines cross on top of the y-axis. Another thing we should well, I shouldn't say another thing. What I was just talking about was different rates of change with the same initial value. So this is what I was talking about. The 2 points, or the 2 lines, excuse me, will cross over each other on top of the y-axis, and that's why their y-intercepts are the same. And then the other situation is, what if their rates of change are the same, but their initial values are different? That's going to be creating 2 parallel lines. Okay, that's not how you spell parallel. Parallel. Okay, 2 parallel lines. If the initial values are different, but the rates of change are the same, which makes sense. If the rate of change is the same, that means they have the same steepness. Remember, rate of change or slope had to do with how steep a line was. So now let's go into one last example. All right, so in this example, it says compare the rate of change and initial value of each function by putting them in order from least to greatest. So I'm finding 2 things here. I'm finding the rate of change and I'm finding the initial value. Okay, 2 things for each. So I'm just going to, off to the side, I'm going to put them in order, but I need to identify what they are first. So in a table, I want to look at how the x's are changing. I see adding 2, adding 1, and adding 3. Don't let that throw you. It may still be a linear function. We just need to make sure the ratios all simplify to the same number. In the y's, I'm seeing we add 8, we add 4, and we add 12. If I put all of my rise over runs, they should reduce down to the same thing. I've got 8 over 2, 4 over 1, and 12 over 3. And yes, 8 divided by 2 is 4, 4 over 1 is 4, and 12 over 3 is also 4. So that's going to be my rate of change, or my slope. As far as the y-intercept goes, I don't see x being 0 anywhere, which means I can't just pull it right out of the table. But I can use the fact that my rate of change is 4 to go back 1. So if I start at x is 1, if I go back 1, if I subtract 1 and go to 0, that means I need to take 2 and subtract 4 from it, because if I add 4 to go from point to point, to go backwards 4, that's how I'd get back to my initial value. So 2 minus 4 is -2. So my equation for function a would be y equals 4x minus 2. I created the equation basically so that I can see the y-intercept and the slope right next to each other. Function b is already in an equation form. So I'm just going to jump straight to function c and figure out what my rate of change and my initial value are here. I'm seeing the line is hitting the y-axis at -3. So I'm going to write a note of that the b is -3. And then I'm going to locate another integer value point. Looks like we can use this closest one, or I'm seeing another one over here we can use as well. I'm actually going to use, there we go. I'm going to use this point and this point. I think that'll be easiest to count. So, and remember, it looks like the scale is by 2s. Each tick mark is 2. So this would be a rise of 2. And then the run would be 4. Rise 2, run 4, simplified would be 1 over 2. So my slope here would be 1/2, making the function rule y equals 1/2 x minus 3. Now we're ready to compare, because all of my functions have a y equals mx plus b written for them, and thus I can really quickly identify the rate of change and slope and put them in order. So I'm going to write off to the side rate of change order, and we're supposed to be going from least to greatest. So those are all my m values. In function a, my m is 4. In function b, nothing's written next to the x, which means it's going to be 1. And then in c, the m is 1/2. So the order that these should go in is function c, function b, and then function a. Because c had a rate of change of 1/2, b had a rate of change of 1, and a had a rate of change of 4. Now let's look at the initial value. Okay, initial values are the b values. So I'm seeing -3, -4, and -2. So I'm going to put those in order now. Looks like whenever we're dealing with negative numbers, remember the biggest negative number is actually the smaller number. So function b has the smallest initial value. Function c is next, and then function a has the greatest initial value. B at -4, C at -3, and A at -2. So let's have you guys give this a try in your U-Try. All right, so that pretty much wraps up our lesson today. We actually compared both rates of change and initial values, and we also interpreted their meanings in context. And actually, we did a lot more than that. We were able to identify the slope and the rate of change, and the y-intercept, as well as compare them in different forms. That's actually really important. We were able to do it in tables, graphs, equations, and context. Please refer back to any of the examples. If you need any help, you may go ahead and start your practice.